Alright, this is notes 3.4, page 2. Alright, so we're talking about average velocity. Average velocity, just think of the change in position over change in time. Okay, change in position divided by the change in time. So it's really just a slope equation, right? The slope of a secant line in between 2 points. So let's say that we have 2 points, t sub 1 and t sub 2. So I could get the change in the position as f of t sub 2 minus f of t sub 1 all over f of t sub 2 minus t sub 1. So the change in position over the change in time. So if I want to know average velocity over a short period of time, I could use this, as the time period got shorter and shorter and shorter, I would be approaching the average velocity over no change in time, which is the instantaneous velocity at a particular point in time. Just like the slope of a secant line, as we let h get smaller and smaller, it became the slope of the tangent line. So this is the same kind of thing. So as we let t sub 2 or t sub 1 approach t sub 2, then we could rewrite this average velocity equation as the limit as t sub 1 approaches t sub 2 of f of t sub 2 minus f of t sub 1 all over t sub 2 minus t sub 1. And you should recognize this as a derivative, the form of a derivative. So that actually equals the derivative of the position function. So the position function was s, so this would be s prime of the variable t, and that's going to equal instantaneous velocity. And we're going to use just the letter v to indicate instantaneous velocity. The velocity at a particular point or an instant in time. Now velocity can be positive or negative, and you need to have a good idea of what the positive and negative velocities would mean. So we can be positive or negative. If velocity is positive, so if velocity is positive, what that tells us is that the particle is moving to the right in a horizontal line, or it could be up if it's a vertical line. If velocity is negative, then that tells us that the particle is moving to the left in the negative direction, or down if it's a vertical line. Alright, so let's use this information about velocity to continue our problem. So we want to analytically determine when the particle is moving left, when it's moving right, and when it changes direction. So when we graphed that on the prior page, we looked at moving right, moving left, moving left, moving right, moving right, moving right. And if you think about it, if something is moving to the left and then changes and moves to the right, it has to come to a stop in order to change directions. So anytime we're changing directions, the velocity at the point that it changes direction must be equal to 0. So we're going to use that to our advantage. So first of all, let me rewrite the function here. We had s of t equals t cubed minus 6t squared plus 9t minus 12. That's our position function. And we can get velocity by just taking the derivative of this. So the velocity is s prime of t, which is just here 3t squared minus 12t plus 9. Now since I'm interested in where the particle is changing directions, I need to know when velocity is 0. So it changes directions at at velocity equals 0. Or it might. Okay? Actually, what I would have to look at is one more thing. It is possible to stop and then continue going in the same direction. So I need to stop and change directions, which means if I'm moving from the left in one condition and the right in the next condition, that means that also my sign changes on my velocity. Because the velocity, a positive velocity means I'm moving right, negative velocity means I'm moving left. So if it changes signs, that means that it changes directions. So here we go. Let's take a look at this. The potential for changing directions at velocity equals 0. So I'm going to set the velocity equation equal to 0. I'm going to try to factor this. I can see that a 3 comes out. Hopefully that helps me factor the rest of it. And actually it does. This does factor. So let's see what it is. I need 3 and a 1, and it looks like they both need to be negative. So there's my factoring. And using the zero product property, I know 3 could equal 0, which it doesn't ever equal 0. T minus 3 can equal 0, so t equals 3. T minus 1 can equal 0, so t equals 1. So those are my 2 times where the velocity would be equal 0. So I need to know if that is actually a place where the direction changes, or if it's not a place where the direction changes. So to determine that, I'm going to look at the sign of the velocity to the left and to the right of these zeros. So I'm going to use what is called sign analysis to find a change in direction. And when I do this, I'm going to create a number line here. I'm going to be concerning myself with the velocity, and my 2 breakpoints are t equals 1 and t equals 3. Those are my points of interest. So all I have is 3 intervals. There are no other places where we could change directions, because that's going to occur only when the velocity is 0. So these are the only places. So I have 3 intervals to concern myself with. I want to know on each of those intervals, am I moving left or moving right? So I'm going to pick a value less than 1, and the easiest one is 0. And I'm going to plug in 0 to the velocity equation and find out if the sign is positive or negative. Now a really nice way to do that is to use the factored equation for velocity, and then consider for each of the factors here, is it positive or negative. So the 3 is always positive. If t is 0, 0 minus 3 is negative. When t is 0, 0 minus 1 is also negative. So for multiplying these 3 parts, I have a positive times a negative, which overall is positive. And that means the particle is moving to the right. In the next piece, I need a number between 1 and 3, so I'm going to use t equals 2. And I'm going to do the same thing, plugging in 2 up here. 3 is always positive. 2 minus 3 is negative. 2 minus 1 is positive. So a positive times a positive is negative. So that means at this point, or in this interval, the particle is moving to the left. So we did have a change in direction at that 0. Finally, we need a value bigger than 3. Keep it simple. Let's use 4. And if I plug that in here in a similar way, I get a positive. 4 minus 3 is a positive. 4 minus 1 is a positive. 3 positives multiplied together yield a positive. And so I'm moving right again. So you're looking at your sign analysis here, and you're looking for a change in sign on either side of your 0. And if you have that, it means a change in direction. Now, creating this is not enough to answer the question. You actually have to provide a summary of your answer. So let's revisit the question. Determine when the particle is moving left, right, and when it changes direction. So I'm just going to do one interval at a time. So I'm going to start with t minus 1. No, t is less than 1. It's moving right. In between 1 and 3, it's moving left. Bigger than 3, t greater than 3, it's moving right again. And then we verified, because of the change in signs, it changes direction at t equals 1 and t equals 3. This is your full answer right there. Now, if we had got the same signs here, we would not be able to classify that as changing direction. We would just report the interval moving right or left as appropriate.